All right. Don't stand too close. Radioactive. Alpha or beta, it doesn't matter. We're going to do calculus. Going to be radioactive. All right? Remember that decay process doesn't matter if it's alpha or beta, doesn't matter if we're doing algebra or calculus. The rate at which it decreases is a change in nuclei over time. All right, so that's what we're going to do is set up a differential equation for the change in nucleiuses over time. The rate at which it changes right there is how active it is, which you learned in the algebra section is simply a lambda n. Remember, lambda is that decay constant, n is the number of nuclei that could possibly break. So a change in n over a change in time is lambda n. I'm going to put a negative sign out in front of it there because it's a decreasing number. That lambda n measured in becquerels, if you recall. Decays per second could also be in curies. All right. So anywho, that rate, what I'm going to do is move the negative sign, and I'm going to separate the variables or get the n's to play Beatles music. All right. So what you'll then recognize is I have an n in the denominator. And remember, when you have an n in the denominator and the numerator is nothing more than that differential, then what you end up doing is integrating an n to the -1, which you all know becomes a natural log. This strategery should look pretty familiar to you by now. I'm sure you've done quite a bit of these, but anywho, you're integrating from some number that you originated with. That's what the NO is. You remember that the N is however many you have at any given time, which that time again started at time 0, went to whatever time frame you're dealing with. So N's downstairs, which means you can rewrite it as an n to the -1. You all know the integral of a -1 is a natural log. I fished out the lambda because it's a constant. Remember, lambda is a constant. You can fish it out of an integral. So what this ends up being is the natural log of n, and you plug in your boundaries, the original and the final, or whatever time frame you're interested in having the number of. T0 to t goes in right there. So this then becomes the natural log of n minus the natural log of n0, the NO, the amount you originally had, lambda t minus t sub 0. Now that t sub 0, your original time, whatever time you started timing, is usually referred to as a time 0. So it's just 0. It goes away. In this particular example, we're subtracting natural logs, which one of my favorite things about logarithmic math. Subtract clearly means divide. So this becomes the natural log of n over NO equals negative lambda t. To kill the log, I'm going to take the E, the Euler's, not Euler's number of both sides. So what it ends up being is this, and you rearrange it in that structure there, highlighted in yellow. Boy, that looks awfully familiar, don't it? There are all sorts of examples or uses for this type of equation. Remember, however many, this is an exponential decrease. Remember, if we're discharging a capacitor, it follows this example. If you're charging it, it's the 1 minus that, but these are decreasing, so we're not going to have the 1 minus in this example. And remember, it's however many there are, is how many there used to be, times e to the negative lambda t. Now that lambda, remember, is a k, was e to the negative kt is the generic term for it. That lambda is our constant, and it's based on time. Remember, I'll show you where that lambda comes from in a bit, but from the algebra video, we said lambda is just the natural log of 2 divided by the half-life. So there's your constant. That's what it is, just a negative kt. That's it. All right, and that's the rate at which they decay, or the number you have at any given time. So if you want to know the rate at which it decays, how active is it, how eager is it to do something, remember the rate is just how the rate at which the n is decreasing as a function of time. So if I can take this n and take a derivative of it, I can get the rate that that n is changing over time. And it's kind of basically what we started out with, that differential n over a differential d. That's all. Instead of a triangle, it's a d. Lambda n. Now remember, that n is something we can have a Swapartuna n for, because that n is what we just got an equation for, is and it. So it's no times e to the negative lambda t. That's all of this together here is r, which is the rate at which it decays. All right. Oh, is a Swapartuna n. So where that no is where that n is what we plug in. All right. Lambda no. What do you know about lambda no? Well, a lambda n is how active something is, the rate at which it decays. So what's the difference if it's a lambda n or a lambda no? Lambda times any given n is how active that sample is at that time. So we can replace lambda no with the rate at which it's initially decaying, which was R-O. So that O, again, just means the original rate at which it was decaying. Whenever that radioactive sample formed, how active was it at that time? That's what RO is. So this becomes a differential n with respect to time. That's the differential n with respect to time. That's the rate at which it decays. This lambda no is what becomes the RO, and as times e to the negative lambda t. So the rate at which it decays at any given time is the exact same formula. Just swap out the n's for r's. Now, to tell you where lambda comes from, this is a calculus arrival at a lambda. It's just by definition a natural log of 2 based on a half-life. All right, the half-life is what I should say. The definition of a half-life is simply the amount of time for n to decrease itself by 1/2. So the amount you have would be the amount you started with divided by 2. So all I'm going to do is just take that n original and divide it by 2. Now remember, the activity is a lambda times an n. The lambda stays constant. That's why it's called a decay constant. So since lambda is constant, if n decreases, then the activity also decreases, the rate at which it breaks. So 10 pounds of the stuff breaks faster than 1 gram of the stuff because lambda stays constant, but the n, the number of those molecules, decreases. So it's the rate at which it decreases is also cut in half. All right. So what I'm going to do is start with that rate formula I just highlighted. R is RO times e to the negative lambda t. Now what I'm going to do is I'm going to say, well, that R is going to be half of the original. So all I'm going to do is just call it half of RO equals RO e to the negative lambda t. Now as soon as I put the number 1/2 there, that t becomes the half-life. That's the definition of a half-life. Now I have a very specific time that I'm interested in calculating. The time for this to be half of that. All right, that's where that comes from. So again, you can kill the ROs, which you knows can happen there. This becomes 1/2 is e to the negative lambda t 1/2. That t 1/2 again is just the symbol for the half-life. What I'm going to do is take the natural log of both sides. I end up with the natural log of 1/2 is the negative lambda times the half-life. You guys all know the divide means push the minus button for this particular example. So ln1 minus ln2 is negative lambda t 1/2. Natural log of 1 is absolutely nothing. It's what war is good for. So the natural log of 2 becomes negative lambda t 1/2, which means you can accentuate the positives, eliminate the negatives. So that half-life is the natural log of 2 divided by the lambda or the lambda is the half-life divided by, or I'm sorry, the lambda is natural log of 2 divided by the half-life, which I guess is how I should write that, isn't it? So you can, here, let me, boop, there you go. So that is the formula that I want you to remember. So those are the three equations. And here, let me rearrange this one to the where lambda is T1/2. Okay, that's how you get those. So let's pretend in our heads we have this sample problem, 10 grams of anything. It don't matter. It could be any given mass unit, 10 pounds, 10 kilograms, 10 moles. It could be a number, 10 anything of plutonium-239. Huh? Just an example I gave. How long will it take for it to be reduced to 1 gram or 1 of whatever it used to be, or what we'll end up doing is making a ratio 1/10 of what it used to be. I'm going to look up the half-life of plutonium-239 from that same website I showed you. It happens to be 24,360 years. That ain't bad. So to get our decay constant, that's what we're going to do is figure out what lambda is. Remember, it's the natural log of 2 divided by the half-life, but that half-life needs to be in seconds, all right? So that's going to be annoying, 24,360 years. That's a lot of seconds. Take the natural log of 2 divided by 24,360 times the number of days, times the number of hours, times the number of seconds. That happens to be this number. So that's the decay constant, 9.02 times 10 to the negative 13th per second. That is not the activity. That is the decay constant that you could use to calculate the activity based on the amount of molecules, or I should say nuclei, of that isotope that you have. Now, set up the N equation. The N is equal to NO times e to the negative lambda t. What I say, we're going to set up a ratio. This one happens to be 1/10 of the original amount. So it said 10 grams decaying into 1 gram. Now you have a ratio. 1/10 of the NO is what N is. NO to the negative lambda t. So there's that. You can kill the NOs. You've done all this before. The NOs die. 1/2 or 1/10 is equal to that. Take the natural log of both sides. You know it becomes a natural log of 1 minus the natural log of 10. Remember, the natural log of 1, again, is what water is good for. Absolutely nothing. You can eliminate those negatives here when you push the divide button. The amount of time that it takes is that natural log of 10 divided by 9.02 times 10 to the negative 13th. That was our activity, or that was our lambda. 2.5 times 10 to the 12th seconds. All right, so that's how much time it will take to decay into an amount that is 1/12, or I'm sorry, 1/10 of what it used to be. Now, that's not a very friendly time unit. So what I'm going to do is I'm going to convert that to a more friendly time unit, 2.5 to E12 seconds. There are 3,600 seconds in an hour, 24 hours in a day, 80,000 some odd years, 81,000 years. All right, that's going to be there a while. All right, so things with half-lives that are in the thousands of years like this, there's where the stuff that's dangerous. Remember what I said before. If you have a half-life that's 200 billion years, you're probably going to be fine. That's pretty darn stable. If you have a half-life that's nanoseconds, picoseconds, it's going nuts, but it's probably going to decay pretty darn fast. You'll be all right in a couple of minutes. But this stuff is going to be around for a while. So that 80,000, 81,000 years, well, get used to it being there, kids. All right. But anyway, that's a calculus version of what we were doing. So again, please remember the 3 formulas, which again is this, the N, the R, and then that lambda is, again, you can think of it as the same thing as the time constant for capacitors, charging, discharging, inductors, inducing and deducing, that sort of stuff. But this is the calculus version and where half-life calculations come from. So you had the algebra and the calc, and for that we well, right there, we're radioactive, eh? Yay, physics.